YouTube now. So, welcome everybody. I'm David Greenberg. I'm coming to you live from Hamburg in the first online machine learning seminar of Helmholtz Centre Geesthacht. I've got Marcel Nonnenmacher here with me, and together we make up the new model-driven machine learning group at Helmholtz Centre Geesthacht. It is a beautiful sunny day in Hamburg, and we are hopefully all indoors. Marcel, how are you doing?
I'm doing great, thanks, David. Hello, everyone.
So, as we said, please feel free to react, pose questions, or join in the chat at any time here or on YouTube. So, I'll quickly go over our agenda, and then we'll get started on a few of these topics. I'm very excited to go over this really interesting paper we're doing today. So, first of all, we're going to start off with Tobias Weigel from the German Climate Computing Center, who's going to explain the new high-level support team for machine learning and artificial intelligence starting up there as part of the new Helmholtz AI unit, and its role in providing support, training, and infrastructure for machine learning. Then we will discuss the paper Hidden Fluid Mechanics, Learning Velocity and Pressure Fields from Flow Visualizations by, I hope I'm pronouncing this right, Raissi et al., Science 2020. Then we're going to open up the discussion. We're going to plan so there's a question just now in the YouTube chat, is there no video? There's no video of us. What you're seeing in the background on the YouTube live stream is a screen share, and we will be showing some figures and papers as we discussed there. We're going to open up the discussion after going over the paper, and we're going to plan for future meetings and topics. We're going to see what everyone from the Hamburg, from the HZG community who's interested in machine learning, materials science, earth science, other topics, what we're all interested in. We're going to talk about potential papers, speakers, plans for future meetings, and we're going to share any useful links or resources for machine learning and AI topics in and around Hamburg. And then for people who really want to get into the more technical details of the paper, we're going to discuss briefly a follow-up, or rather an earlier paper by the same group, Physics-Informed Neural Networks, and we'll get a little more into the math, the programming, and talk about how it might scale to different problems. With that, I think I'd like to turn things over to Tobias. Tobias, if you want to unmute and screen share your presentation, I will then kind of bridge that over to the YouTube live stream.
Okay, thank you, David. Hello, everyone. Can you hear me?
Mm-hmm.
Yes, David, you can hear me?
Yes, I can.
Okay, so let me share the screen. Okay, so I hope you can see my slides now. Let me know if this does not work. You just get the box off. Okay, so my name is Tobias Weigel. I'm working at the German Climate Computing Center, or the Deutsches Klimarechenzentrum, DKRC in Hamburg. What I'm here for today is just give a very short introduction to what we now call the AIM consultant team. Just to explain what this is, so AIM stands for the Artificial Intelligence in Earth System Modeling sub-project of the overall Helmholtz AI, Helmholtz Artificial Intelligence Cooperation Unit platform. And this is a sort of a sub-project, a shared effort, where both HZG and DKRZ are involved in with 2 teams, and also other Helmholtz centers with individual researchers contributing to this. So I will give here an overview of what the consultant team provides in terms of services, how to get in contact with us, and what we can basically do for you. So to start this. As I said, the AIM is basically structured into 2 parts. One is at HZG, one is at DKRZ. At HZG, we have the Young Investigator Group chaired by David, who will look into actually applying the machine learning methods for providing these benefits we all hope for applications in Earth system sciences. Whereas the consultant team that I will lead at DKRZ will provide counseling, so guidance, conceptual support, but also trainings and technical support and many other things. I will go into the details of that over the next few slides. In support of machine learning and AI services, applications that you as the researchers basically can bring to us at any point. What is important here, that the consultant team serves basically all Helmholtz centers that engage in AI and machine learning methods in Earth and environment. So it's not just that we work here as a team for just the Young Investigator Group, but we work for all Helmholtz centers. If you come to us with problems in this area, we will try to help you. What is very important now is that while the Helmholtz AI project has sort of had a ramp-up phase also over the last couple of months, also in 2019 already, but the consultant team is now operational. So we will have 2 first actual AI consultants getting hired just 1st of April. They will start their work then, and we will then fully be operational. But I'm already now talking to individual centers for first items and so on. The team itself is connected internally to existing DKRZ units, so it's not a sort of something that is just attached to DKRZ. It's fully integrated. In particular, this means that we have sort of an embedding with the user support, technical services. That means access to the supercomputing system, the data system, all the other possible data sources, any kind of other services that are in that area. And at DKRZ, there is also since last year a new AI research group headed by Christopher Cardo, where we will also have some exchange with them on the research aspects related to AI and ML. As I said, the consultant team is there for you. That means we are open for requests from all Helmholtz centers related to AI and ML in Earth and environment. What means that we also help you to formulate questions and so-called vouchers, which are the main currency we currently deal with in terms of user requests. And we work collaborative with you on the scientific cases that you bring to us and basically help you with applying machine learning and ML in the best way possible. As I said, this is a collaborative effort, so we are there for you. This is just a short overview, a very high-level overview of the kinds of services that this could involve. One item from sort of top left to bottom right, the first item is that we will provide and curate a knowledge base with information related to ML in system sciences. So basically the case here is that we help you to help yourself. This is a growing effort that we will start actually with just from the beginning. Then secondly, the technical implementation support. So we basically make your code work. That means on the supercomputing system, on DKRZ, on the visualization cluster that includes GPUs, for example, but also doing something like help with the libraries that you need with PyTorch, with TensorFlow, and all the other nice things. Bottom left, we also provide some training and knowledge exchange. So just earlier this year, we had a first workshop that also served as a kickoff for the AIM sub-project. The idea here is that we lower the entry barriers for those researchers who want to apply the ML methods but don't know where to start, don't know which library to choose, where do I get my 101 course on TensorFlow. So this is also something that the AI consultant team will provide, both with online seminars, for example, but also as individual consultancy items by Skype or something else. And finally, the bottom right box, the counseling. We help you to work with confidence. That means some more conceptual things like dealing with uncertainty, dealing with biases, with the limitations that machine learning methods inherently possess. This is something that the team will need to build up as well, just for a bit. So it's not something possibly right from the start, but it's something we are also working towards. To give you a bit more overview of what this individually means, this is just, I won't go through the details here, but just looking at this slide, you can see, if you're wondering what items you would get help on, these are just examples of how to think about this, on which cases to contact us. One important thing here are the so-called vouchers. This is sort of a project management term that the Helmholtz AI Central Unit has come up with, which basically means that in order for us to work with you on your cases, we sort of need a formal request to do so. And this is what they call a voucher. So in practical terms, what does this mean? It just means that we will also help you to set up some kind of problem statement document where you say, look, we have this challenge to deal with machine learning in some form. We are in need of these kinds of services or of this kind of guidance. And then we will just have a first conversation, for example, via Skype, to figure out what exactly is needed, what would be rendered from the consultants team to you. And then this sort of goes through a process that Helmholtz AI Central has set up for approving these vouchers so that we can then start the actual work. It sounds quite a bit complicated, so don't worry too much about it. It just means that most of the technical implementation support, this is why also this box here is slightly shifted to the top right position, goes through these vouchers. So with actual, just at the current point, we have already some first drafting vouchers in draft state. With David from HZG, but also with colleagues from UFZ in Leipzig. We are also working on that, and I hope that some more vouchers we will get into some draft state over the next weeks. Now, just two more slides on what is actually available just right now from DKRZ in terms of services already available to users who want to deal with AI and ML. This slide is just an overview of the Jupyter Hub instance at DKRZ. I hope you are well aware that Jupyter Hub is one of the key environments and tools where you can just code and prototype some ML applications based on Python and the various libraries I've already mentioned. This is a site that a colleague has provided, who is responsible for this service, operating this at DKRZ. The fundamental thing here is, again, I won't go through the details here. You can look up there. There are also the links. I will provide the slides later on. There are links to the documentation on our website. But you can essentially use our Jupyter Hub instance already now to run jobs on the Mistral supercomputing system with access to specific data sources, for example, CMIP data, but also Cortex and Riclis, with Slurm integration and so on. One thing I want to highlight here. It's on the bottom of the slide. Coming soon, Jupyter Hub 2.0. So the colleague is already working since several weeks and months now on a new instance that will provide many more interesting things, particularly so-called enhanced kernels management. What does this mean? That means that the individual libraries that you need for your applications, you can provide them in a much better way. Then there is some containerization in the background that is currently being set up. So you can actually work with your own custom Python environments there with the libraries you need. And also shared workflow repositories is another thing that's very interesting for the long term, because we are also interested just to collect relevant and interesting workflows, examples from the community, examples that we use in training, and provide them through the Jupyter Hub then 2.0 instance. So this is coming soon, as it's set here. It will take still a bit of time, a couple of weeks, maybe in the summer sometime there will be a launch, and this will include these new functions. Now, one question that was already brought to us was what is going on with access to the actual DKZ resources here. So how do you gain access to the facilities that we already have? The current stance is the Mistra supercomputing system that is at DKZ since a couple of years now will be replaced with a new system next year. But this already includes a GPU or visualization nodes cluster. So parts of Mistral are already equipped with GPUs from NVIDIA, integrated with InfiniBand with the other nodes that are just the CPU nodes. The link that is provided here can tell you more about the specific configuration, how much memory you have on each node, for example, what exactly which chips were used from NVIDIA and so on. But as I said, this is already available now. You can use it also through the Jupyter Hub instance for larger scale ML experiments that are basically larger than just your application on your local machine. How do you get access to this? It requires association with a DKZ project. But currently no application for computing time is required to get access to the GPUs. So I've confirmed this with our support people already, and this is the current state. It could change in the future if there's more demand, but so far it appears that we can handle this quite well informally. So if you have already needs for something like that, then just get in contact with us or with the DKZ support team, and you can get access to the GPU nodes on Mistral. And that's basically it. Just some final thing here. Again, we're very happy to be directly involved in your projects. So we are just not sitting here and doing some consultancy, as the name could imply. No, we are here for you, for working collaboratively in your individual science cases. And we are very happy if you can contact us at the given email address, or just contact me via Skype, via email. And yes, so basically, please come to us with your problems. It's all virtual for now, but that may also change later in the year, of course, we hope for. But basically, we are available now. Thank you. Any questions?
Thank you very much, Tobias. Let's look for questions on the YouTube and Skype chat. If anyone wants to ask a question before we move on to the paper. Yeah, Leonard, if you want to just unmute your mic and ask.
All right, here I am. I just wanted to ask real quick. I mean, I'm not at GFZ. Is that consultation available for other Helmholtz centers? Like that mail that the mail address that you just showed, is that available to other Helmholtz centers as well? Or do we have to go via some other channel to reach you guys?
No. If you are at a Helmholtz Center, then we are officially able to help you with your problems. You don't have to be a sort of part of the AIM project or part of Helmholtz AI. So as long as it's Helmholtz, we can serve you.
All right, that's cool. Thanks a lot.
Linda, yeah, please go ahead.
Yes, Linda.
Yes, I have a question. In what way is what you're providing now overlapping with what Beratung from DKRZ is providing us when it comes to support in using Mistral and in these cases.
Yes. So think of us as a specific subunit of the Beratung. So if you would now go to the Beratung and ask them, hey, I have an application here, I need a TensorFlow, something like that, they will surely get to us then.
Okay.
So it's internally it's connected. So
Okay.
don't worry. I mean, you can contact us either way. But if you already know that your case is related to ML or AI, it's maybe easier to go through the address I just showed and contact us directly.
Okay.
But we have regular exchange. Don't worry, no worries about that.
Thank you.
One thing though. It still means that the any questions more generally related to Mistral are of course still part of Beratung, right? So if it's not directly involving ML or AI, it goes through the normal channels. But that's also not something I think you should worry about. It's just the question of who is responsible for taking up your requests and how this gets handled internally in DKRZ.
Okay, thanks a lot, guys, and thank you very much, Tobias. I think if people have more questions on these topics, let's come back to that in the general discussion, and let's move on now and discuss this paper, which I, for one, am very excited about. Marcel, do you want to join in and moderate this together with me?
Sure, no problem.
Great. And I hope all the audio and video is working on the YouTube stream as well. If there's any issues, please just write in the chat there. But so far, so good it seems. So this is a really exciting paper for me because it's a paper for a general audience, which I think really gets across the opportunities for combining physical and machine learning streams of data analysis and reasoning. And I think does it in a very visually compelling way, and I think it's going to be really, really useful. So I think I want to start off maybe with what are they trying to do? What would be the normal way of solving this problem, and what have they come up with that's new? Because I think it really is a quite new approach, even among the set of approaches which combines machine learning with physical modeling. So I'm going to start off, and this should be visible on the Skype as well as the YouTube live stream. We'll start off with this figure. So on the left, we can see the sketch that was done by Leonardo da Vinci where he shows his streamlines of a flow around an object. And this is kind of what they're trying to find. They want to come up with the flow of a fluid that will explain some data. And the data in this paper is generally concentration of something carried by the fluid. So you have concentration of some marker, of some smoke or tracer in a fluid or a gas which is moving around. And if we can make a few observations scattered in space and time of this concentration, this C here in figure 1b, we want to use those observations to figure out what was the velocity of the flow at each point in space and time, what was the pressure that's driving this flow, and what are the streamlines? So how will a particle in this flow move over time? And this is what they do. So in this example, they say, what if we observe this concentration over time and space? Here's a snapshot at one time. And in order to generate this observed data, they did a simulation with a standard fluid dynamics solver, which includes pressure, which includes all these streamlines, but they don't have access to this. They only have access to the concentrations. And what their method successfully does here is it comes up with the velocities and the pressure of the flow at every point in space and time. So how do they do this? So I think it's interesting to compare how you would do this if you didn't have this new technique. So I want to put up a figure from the European Centre for Medium Range Weather Forecasting, explaining the 40 var method. Now I know a lot of people in the stream here might not be so interested in weather prediction, but I think in terms of how do you adjust the initial conditions or parameters of a differential equation to match your data, this is a really illustrative concept, right? So imagine we have some observations represented by these green circles here, right? And here's time, and then here's the units of whatever we're observing. In their case, it would be something related to weather and weather prediction. And we have a model, a differential equation, represented by this blue curve. And we obtain this using equations for the differential equations, the differential equations themselves, and we solve this with a numerical integrator. We do a lot of computational work to obtain the solution at each time point, but it doesn't match the data too well. So in the 40 var method, which they're describing on this website, the European Weather Forecast website, you differentiate through the output of the numerical solver with respect to model parameters or initial conditions. And this is a very difficult task. It requires a lot of work to implement as a program. It's very model specific, and it's not easy at all. But once you've done that, you can say, if I perturb my initial conditions, or if I perturb the model parameters, essentially the rules of physics in this system that you're modeling, how will that affect the outputs at each of these time points where we make an observation? And then we can calculate how we should adjust those parameters and initial conditions to get a good match to each of these observations, so that we can adjust from the blue curve, we make an update, and we get the red curve, which has got a closer match to the observations. Okay, so this is kind of a standard way of doing it. It's very difficult. It's very model specific, and it involves a lot of, every time you change the thing you're trying to estimate, your initial conditions, your parameters, every time you do that, you have to reintegrate the whole numerical system. What these guys are doing here is actually very different. So if we go back to their text, we can see they're defining a neural network function, which takes as inputs time and space, and it outputs some properties of the flow at that point in time and space. So it takes a total of only 4 inputs, and then it outputs 5 things. The concentration, in this case it's a 2-dimensional example, so the vertical and horizontal velocities, u and v. In this case, 3 dimensions as well, so w as well, and the pressure, right? So it basically maps from space and time into the local properties of the flow. So it's essentially taking over the job of numerically solving the system. We don't actually have to compute the solution at each time point. We're just going to jump to wherever we want to go. So this is very ambitious, and it almost like sort of strains credulity that it's possible, but they're doing it. They're doing it right here. So for each one of these points in space and time, space, and for a given time, they're actually computing the concentration, and they're getting exactly what they should compared to their reference simulation done the old-fashioned way. And how are they able to do this? They're able to do this using this special objective function. So this has got 2 terms. First, we're saying that the observed concentrations should match the outputs of the neural network here. So for every place where we observe the concentration of the system, we're going to, in fact, let me scroll down to the figure 2. It gives kind of a nicer graphical explanation, right? So for any space and time inputs, so we have 3 numbers that go in. The activity courses through the neural network, and out comes concentration, horizontal and vertical velocities, and pressure. And so we want the concentrations to match our data. We can see the example here. This is a stream in 2 dimensions, a flow around a cylinder, which blocks the flow. And then we get this wake here. And if we only observe the concentrations over time in this little flower-like pattern with a black outline, we can actually reconstruct the entire flow. So how does this work? So we want to be able to put in any space and time where the space is inside this flower-like pattern, and it should match the observed data, whether we have a lot of it like in this example or just a little bit, we have it more spread out in space and more spread out in time. But this is not the only constraint, right? We don't want it only to match the data. We also want it to follow the laws of physics for this system. So we have the equations for this fluid flow. It's Navier-Stokes. And this basically says that the right-hand side of each of these three terms of each of the second two terms should be 0. And then the third, this last row is basically saying that the flow is incompressible, right? That the divergence at each point is 0. And so if these three right-hand sides are 0, then the flow obeys the laws of physics. So what they'd say is, well, these should be 0, not only at the places where we have data, but in fact everywhere. So if we sample a place we have data, the output of the network should match our concentration. But if we sample any point in space and time anywhere, then these right-hand sides should be 0. So then we go back to our objective function. Right here, we see these two terms. 1, we should match the data. And 2, we should follow the laws of physics whether we have data or not. So this is a basic concept of what they're doing. So I want now to maybe pause a little bit, take questions, see if that's clear for everyone, and then I'll hand it over to Marcel to explain exactly how they compute this objective function in terms of auto differentiation. So any questions so far, or anyone want to call attention to anything in the paper and guide the discussion in some direction? Well, if no one has a question or a comment so far, then Marcel, do you want to talk about auto differentiation and how they use this here?
Wait one more moment. People to come up maybe with a question.
Yeah, let's wait a bit more.
Okay, then, so generally, auto differentiation is an idea. Usually it's implemented in some form of high-level programming language that allows us to automatically get differentials, partial differentials, of functions that we write down in a programming environment without having to actually analytically compute them and code them down separately. So the idea that this works on is that you have a high-level programming environment. So for Python, this would be mostly PyTorch and TensorFlow these days, which is essentially just aware of the product rule of differentiation, and which uses the fact that most of these functions that we work with, like neural networks, or also the Navier-Stokes equations in this case, they're composed of relatively simple operations like adding, multiplying, maybe an exponential, of which we know what the differential looks like. And then with the product and sum rules and quotient rules, we can just combine the differentials of the individual parts and plug them together to get the differential of the whole function. In particular, with neural networks, this is very, very convenient because these are just, especially if you have a deep network, these are stacks of many, many cascaded linear and nonlinear operations So they're very simple, that all have the very same differentials, but if you were to write this down, this would be very lengthy expressions. But the computing environment of an autodifferential environment automatically keeps track of that and also then efficiently computes the gradients. Why is this particularly noteworthy in this case? I mean, it's certainly true in all of deep learning, but in this case, if you look at say figure 2 of the science paper, where we saw the neural network, you see on the left side you see the neural network, and on the right side you see the Navier-Stokes equations, or the conditions derived from them, and there you see that you, for instance, have in the first row for E1 you have terms like Cx, Cxx, Cxy. These are partial differentials of the output of the neural network with respect to some of its inputs. So if you look at the gray box in panel C, on the left side you see the neural network. You see it has, in this case, 3 input units, T, X, and Y, and it has 4 output units, C, U, V, and P. And for the Navier-Stokes derived conditions, E1, E2, E3, you need the partial differential of C, one of the network outputs, with respect to X and Y, which are two of the network inputs. And an autodiff environment also gives you this for free, essentially. Just as you compute gradients of the network weights during training, you can also compute partial differentials of the network output with respect to the inputs. And in this case, combine all of these to get the loss in equation 1, which then takes gradients with respect to both the output C and with respect to these partial differentials of the output of C with respect to some of the network inputs.
So Marcel, there's a couple questions from the YouTube stream. Eduardo is asking, first, let's do the second one first. He's asking if the gradients are computed from Python code.
Excuse me, I'm having some troubles with connections. Can you repeat?
The question is, are the gradients computed from Python code? How are the gradients, what are we giving to this whole algorithm to get the gradients out?
I'm sorry, it's really bad right now.
Let me quickly take over then. Just pipe back in when your connection's back. And if anyone can't hear me either, please say so in the Skype or YouTube chat. So the question is, how are the gradients computed? So the model itself is just a sequence of neural network layers applied to the input data. So we give it the inputs X, Y, and time, and we get all these outputs out, and we do it all on a point-by-point basis. So even if we're dealing with very large systems that span space and time, the inputs and outputs are always low-dimensional for this network. And now the network will be implemented in a machine learning framework, usually inside Python, and that'll generally be TensorFlow, PyTorch, etc. In this case, the authors used TensorFlow. So it's kind of a specific library inside of Python, and all you have to do is express the architecture, how the units connect to each other. And then once you've expressed that, in fact, we can even have a look right now at their code, which they've been gracious enough to share online. You can see the inputs defined with respect to the outputs. Let's see if we can. Yeah, so we have definitions of the neural networks like here. And then once you've defined that, you can compute outputs for inputs, and then automatically you can also calculate gradients. So you really don't have to express any of this yourself. But it is basically, it's not analyzing the code, it's rather analyzing some computations that happen under the hood the computation graph, as we would say in machine learning. The other question from the YouTube chat is, can the neural networks extrapolate in time? And yes, they can both extrapolate and interpolate in the examples we've seen here, right? So if we look at where is the training data, right? We only observe it in this little flower, this outline, this little spatial region outlined in black here. This is the only place in space we observe anything. And then here they train the method with two examples. One, where we observe concentrations inside this flower region all the time over here. And in the other case, where we observe them only intermittently. So there are long periods of time, for example, for over 4 seconds here, we don't observe any data. But what we see is that the network is able to reconstruct the concentrations in between the observations, as well as outside of the region where we observed anything. So in fact, and we see a few more examples of this in this group's other papers as well, in fact, it can extrapolate in time. And how does this work? Well, basically, in order to minimize this objective function consisting of two terms, right? If it succeeds in minimizing this and getting a low value, it means for one thing, it's going to match the data. But for another thing, it's going to match the physics. The way the output of the function changes in space or time has to satisfy the rules of the differential equation. For example, this Navier-Stokes in 2 or 3 dimensions. Here's one example right here, these differential equations. So if it does that everywhere, it means it has to follow these solutions as valid physics as it moves away from the places where the initial conditions or the boundary conditions or the concentrations as data are known. And this allows it to extrapolate and interpolate very effectively. And the way the authors of the paper describe this is quite interesting. So often when you have a neural network function, you're learning some relationship between variables with a neural network, you add regularization. You say, oh, I'd like my weights to be as small as possible. I'd like to even use as few layers as possible. There's a lot of different ways of doing it. You can use other fancier tools as well, like dropout or batch normalization. And the authors basically see the requirement that the output of the neural network matches the known physical laws as a kind of regularization, which allows them to deal with less data and to extrapolate and interpolate a lot better. So, and it's very interesting how they use the auto differentiation to do this, in that auto differentiation is a tool which is developed for one purpose, mainly for minimizing the objective function that you want to minimize. But here we're taking this existing tool, which was developed for all sorts of purposes in minimizing all sorts of functions in all sorts of different ways in machine learning, and we're reusing that tool for a different purpose. Instead of using auto differentiation to differentiate and thereby minimize the objective function, we're actually using auto differentiation to build and define the objective function. Another interesting contrast from a lot of other machine learning techniques is, even though we're dealing with images, there's no convolutions, there's no high or dimensional inputs or outputs. When we make a pass through the system, we're only doing it for a single point in space and time. We're never passing multiple time points or multiple points in space through the network at once. So how does it work? How do we get coherent solutions? Because we're imposing, using the known laws of physics, the correct rates of change in space and time. And this leads to overall solutions that match our physics. So it's also sort of interesting to ask, what are the advantages or disadvantages if we compare to, say, if we go back to this 40-var approach. Let me pull this up again. Oops. Yeah. Right, so here we have to, every time we adjust, say, the estimate of the laws of physics or estimate of the initial condition, we have to immediately recompute the entire numerical solution starting from the beginning. Whereas in this hidden fluid mechanics approach, we get an instant mapping of inputs, as in space and time, to outputs. We don't have to numerically compute the solution from the initial conditions. We can jump to the solution at any point. This also means we don't have to store large solutions in memory if the solutions are very large. On the other hand, it's useful to ask, what is this network learning? It's not learning to solve the equation, it's actually learning a specific solution for the equation, right? So if we look at this beautiful image of the flow with all the streamlines, with the pressure gradients, all of this information has to be stored in the neural network weights of this neural network. It has to be stored in the learned weights inside this architecture. Whereas if we look at, say, another approach, for example, neural ordinary differential equations, this came out a few years ago. Here, the neural network instead learns the tendencies of the system, and it doesn't have to represent the entire space of the solution in space and time. It doesn't have to represent all that information. It only has to represent the rules describing the physics. So it actually is storing a lot less information in its weights. It's possible for each of these approaches to have advantages or disadvantages depending on the context. With this neural ODE approach as well, where you learn the ordinary differential equation, you again have to compute the solution every time you change the weights, every time you change the parameters. You have to numerically integrate the solution over and over again, which we don't have to do here. So it definitely fills a different kind of niche to what was available before. In addition to the simple 2D example based on Da Vinci's drawing, and in addition to this flow around the similar in 2 dimensions, you can see they explored the number of observed concentrations in space and time versus the number of time points where they observe. They do kind of an analysis of how many points you need to observe and how many time points. There's a lot more of this in supplementary methods. We won't get into this now, maybe when we get to our technical discussion later. And then they also go to 3 dimensions. This is a nice medical application where they're modeling blood flow through an intracranial aneurysm. So they have everything in 3 dimensions, and it's a simulation. It's not real medical data, not yet, but they're trying to move it more in the direction of what you could really do, what you could get access to. And this is in some ways a much more difficult example, as they point out, because we're trying to model something which is internal instead of external. It's much more difficult to observe it. You can't make easy observations of pressure and in this very delicate tissue. But what they ask is, if you were able to observe the concentration of blood in these 2 orthogonal planes, could you then compute the flow, the pressure, the velocities, and the concentration everywhere? And the answer again is yes. Using the small amount of data, they're able to solve for all these hidden variables and come up with a neural network which takes 3-dimensional space and time as inputs and generates concentration, pressure, and flow velocities as outputs. And then we can follow his streamlines. We can see the simulation ground truth used to generate the observation data. We can see all the streamlines here, and we can see very similar looking streamlines for the flow that they infer using their neural network. And there's some criticisms one could make. The level of noise is very low. They never really look above 1% observation noise, so in a real medical context it could be much higher. But I think it's a really it's a different approach, it's a powerful approach, and I think that's probably why it belongs in science. So I think we've covered the basic concepts. I want to discuss a little more about what this method can and can't do, when we might want to use it, when we might not want to use it. But first, I just want to open it up to questions. Is everything clear? Is anything not so clear? Or does someone want to raise some other topic? So I would pose this question to the group, especially to the earth scientists among us. Could we scale this up and use it for weather or climate prediction? It would mean adding more variables like temperature and moisture. It would mean describing solutions over longer time points. And it's actually something I have no idea. I'm very curious about it. What are the limitations? Does it make sense? Would it scale? Would it not scale? Is it a good idea? Yeah, Lawrence, please go ahead.
Hi, can you hear me?
Yeah, I hear you fine.
Yeah, good. So yeah, thanks. Very interesting. Very interesting paper, and thanks that you bring it to your attention. I used to work at Deltares, which is actually an institute that does a lot of fluid mechanics and a lot of computations on flow. And I'm wondering, I mean, this is a very neat approach, but the question I think in the end is where do you get the data to train this type of applications? I mean, in a lot of earth science, I guess in the application that they show, for instance, for medicine, I suppose you have techniques of gathering this data on which you base the regressions. In earth sciences, often the problem is you don't really have this data. You don't have stream flow observations of the actual fluid flows at such a scale and such a detail, because it's just the scale at which we are working is often just too big. It's a continent, or it's even the globe. How heavy is this on the need for observational data, or can you do with very little observational data and still, because you're building it on the Navier-Stokes equations, can you still do decent predictions even if you have few and highly uncertain observational data?
Yeah, I think this is a really great question. If you look at what this group says in their papers, there's really no theoretical basis of why this should work, and yet it really works remarkably well. So maybe this will be more a topic of future research and figuring out when it can and can't work. I think I think a major limitation of this right now is it has no way at all of expressing or dealing with uncertainty. It's just going to find some solution which matches your data and matches your physics. And as far as what you need to observe, it's an interesting question as well. So if we look at equation 1, hopefully that's on everyone's screen right now. So the second term is just enforcing the physics as we've discussed. The first term, so in all of their examples, they assume that the concentration of whatever the advected, whatever the transported quantity is observed at some points with or without noise. But you could certainly replace this with a different objective function, right? So if you look at what is the output of the network, it's outputting at every point in space and time, it's outputting concentration, velocity, and pressure. So of all of these variables, most of them are hidden. We never make any observations of them. Instead, we just observe concentration. But one could certainly imagine a version of this where we don't observe concentration either, where this is also a hidden variable. But instead, we observe something downstream of it. We have some model which is, okay, if we observe moisture, temperature, precipitation, photographs of satellite images of clouds, pressure at surface stations, wind speed measurements from remote sensors, whatever we have, these are constraints. And all the direct the variables which are directly represented in the Navier-Stokes equations, like temperature, pressure, local density of the fluid, these are never observed directly, even with noise. We only have downstream observations. So this is a possibility, and would it still work is a completely open question. I think it'd be very exciting to try this with some simple toy models and ask, what do we need to observe? They do some very rudimentary analysis of how many time points and how many points in space you need to observe in this low noise idealized conditions, as you can see in figure 2b. But I think it's completely an open question, and we don't know the answer yet. Yeah.
David, can I ask you?
Mm-hmm.
Do you hear me? So
yes, I'm sorry. Who's? Yes. Can you want to introduce yourself to the group before you?
Oh, sorry. I'm Andrei Blazenko.
Mm-hmm.
Yeah. Somehow I did this kind of jobs of recognizing slow motions from particle image velocimetry. So I had similar. I used similar approaches, but not with the neural network. It was much simpler. So in fact, you have Navier-Stokes equations in a weak form. So it's your regularizer and the data term. So meaning L2 norm from your observations minus what you try to fit. And yeah, my question, so whether this neural network approach, so whether it's better or not better, so than these approaches.
Yeah, I'm not sure I fully understand the approach you're describing. You're saying you fit some flow field using the Navier-Stokes as a regularizing term, and then what was your data matching? Was it a polynomial, a neural network, something else?
No. So I mean, suppose you measure the motion in tide, or so you have some. So you have some estuary motion or whatever else. You just make a photos of mud, how it's moving in the water.
Mm-hmm.
So it's super noisy, it's super sparse. You just have some particles and you try to reconstruct the motion. This is your data, actually. So you roughly know how the velocities of these particles. You want to, first of all, to remove the noise, and you want to fill in the gaps between this data. So just to get it. So what you do the first thing, you should have some equations that can estimate that, and this is what so this is your estimator, say, and the data, so the observation. So the first term would be data minus what estimator gives you plus estimator as a regularizer. So what I actually see. So they have estimator, it's Navier-Stokes equations. So as a regularizer, similar thing, but as a data term, they use neural network. And it's a little bit different. So it's just with neural network in my question. So what are the advantages in this case?
Yeah, I'm not fully. I think maybe it would be great if what you're describing is published or available somehow. If you could email us to the mailing list, and we'll post a link.
Sure.
In the YouTube description as well, because it sounds worth following up on. They do, in the paper, they cite some of the existing literature. I think a little more in this physics-informed neural networks paper we'll discuss later when we get a bit more technical. But yeah, maybe there's a different way of doing this, and that actually, it sounds quite interesting. So if we just compare directly to doing a numerical solver, it's quite interesting. It's one nice advantage of this is we don't have any grid. There's no discretization in space. There's no discretization in time. Another advantage of this is that as we begin to adjust the physical parameters we're estimating, for example, the Reynolds or Peclet numbers. I'm sorry, I'm not sure if I'm saying that right. Peclet, my French is quite terrible. But as we adjust his physical constants, as well as the weights which describe the flow in time and space, we don't have to start over every time we update them and integrate from forward to from start to end of the simulator. So these are our potential advantages. There's some real differences from other ways you might use this physical knowledge in a neural network or machine learning based approach. So from my own past work and stuff I've worked on with Marcel as well, we've said, okay, we have a simulator. Let's use this to generate simulations and then use these as training data for a neural network, which can be very effective. But an advantage here is we don't actually have to do a single simulation. Instead, the equations defining the model are directly provided to the training procedure of the neural network. So this is a whole different strategy. There's another question in the YouTube chat. Is the code of this network much simpler than a numerical solver? Yes, it's incredibly a lot simpler. So I'll open it again. The code they've shared on GitHub. So this is code here for the 2D cylinder example in Figure 2. So just to pull that up again very briefly, this example here. Here's the code, and it's code not only for the computations, but importing the data, doing some plots, plotting some equations, so really everything. And it's extremely simple. This is less than 400 lines of Python code, spaced out with comments, lots of print statements. The actual training and model are probably less than 200, and I think it's great they shared this data. It would have been a little bit nicer if they'd shared it as a library that you could import or IPython notebooks. But, in this case, it almost doesn't matter because the code is so simple that it's really just very, very short. So this is a very nice advantage of all this. If you have differential equations, ODEs, PDEs, you can really apply this very, very easily. There's just not that much to do. Whether it in general works, where it will work, one is less sure. So, for these small neural networks that they're doing, it's very hard to imagine, say, weather prediction or climate modeling over any reasonable span of time because there's just so much in the solution over time and space, so much information which all has to be stored in the neural network weights. At some point, you're just going to run out of representational capacity. But where is that limit? It hasn't really been explored by anyone in any of these papers yet. So I think, to answer the question, it's way, way simpler than a numerical solver of a differential equation. And then there's some amazing things they do as well with this approach, which we'll get into later when we discuss the second paper. So there's one more point I'd like to make, and maybe this is a question also to anyone with more experience in these spectral numerical solvers for partial differential equations. So I was curious, how long does it actually take to solve these systems, right? So if we go to the supplementary material, we have these nice tables, if I can find them. Let's try to do a search. Not working. Okay. We're trying to find these tables describing how many time steps they did for their numerical solves, and we can compare this to how long everything would take otherwise. Probably we'll find them right at the end. Here we go. So these are forward simulations, right? So for these different examples, we're talking about, so let's say the cylinder in Figure 2, we're talking about 185,000 time steps with their numerical solver, their spectral PDE solver they use to generate their ground truth to compare to. Now, how long did it take them with their neural network? They typically did 1 million steps. So 1 million steps, and it took them basically, some 2 seconds to do 10 iterations, or a mini batch to do 10 iterations took them about 2 seconds, they said. So then if you come down to it, this is about, 55.5 hours for that figure 2 example. This is how long it took them to train the neural network to learn that particular solution. So it's definitely not instant. Now 55 hours versus 185,000 steps on their solver, that would be equivalent if the numerical spectral solver for this PDE took 100 milliseconds per time step. I don't know if that's a lot. I don't know if it's 1 millisecond or 2 seconds per time step. Maybe someone with more experience can chime in and tell us. But it's reasonable to think that maybe they're sort of equivalent. So this is basically all I have to say about this paper. Any other questions about the paper itself before we open up to general discussion about everything? Give a little bit of time. I believe there's a 1 or 2 minute delay on the YouTube stream behind our live Skype call. All right. If anyone has a question, just chime in on the chat, and otherwise, I want to just open up the general discussion about what this meeting is going to be. Originally, it was supposed to be an in-person meeting at Helmholtz Centre Geesthacht with occasional meetings in Hamburg that we would also put online. And maybe people could call in or do a live stream. Now, of course, it's going to be online only for the foreseeable future. But I want to pose the same questions I would have posed in person, which is kind of, who are we? What do we want from this? And what do we want to do next time? So I'd love it if anyone wanted to chime in, what they want to discuss, what they want to get out of it. Do they want to build up their skills? Do they want to get more of a sense of what's happening in the literature? Do we want to bring in people to give talks on their own work? Do we want to do some hands-on tutorials or collaborative coding projects? What are people interested in?
David?
Yes.
Well, in my view, I think we would need a mixture of all of these things that you have mentioned. So, for instance, today's, for me, many things were new, and I guess that for many other people in the virtual meeting were also new. I guess that there are many aspects in machine learning that I'm not aware of, and everyone would be enlightened if we could also continue this sort of seminars like today's seminars. So discussing a paper with new aspects in which we can learn quite a lot. But at the same time, I think it would be also useful to have some type of seminars with a more practical utilitarian approach, in which we really solve some specific application, some specific problem, and we go through until the end, or basically, let's say, as much as possible, looking into the code and learning coding tricks and things like that. I think we need all of these things, and perhaps later on when we could decide if we have to focus on something more specific. But I think at this point we'll have to actually to have a wider scope and try to first lift our capabilities in machine learning, and then perhaps discuss more the specific.
Oh, thanks. Great. Tobias, you have some comments as well.
Yes. So first, what Edu just said, I would like to second. I think a mixture of looking at papers, looking at specific problems, but also possibly looking at code at some point, some specific examples. I think that would be great to have that wide coverage from the conceptual things to the really pragmatic, dirty hand things. Secondly, I was wondering what the audience scope of this meeting would be. So of course, with the Corona situation, we are doing this virtually online anyway, at least for the next I don't know, few weeks or what. But thinking about this, and this was also questions put forward by the colleagues from Helmholtz AI Central. Does this meeting should we open it in general to just beyond the local sort of Hamburg Geesthacht scope, or do we want to make some alternating things, like every 2 weeks it's rather a bit local focused, every off week it's a general webinar? Or is it in general open to anyone, and we also advertise it as such, or we don't, or it is open but we don't advertise it too strongly because it raises expectations? I mean, all of these considerations could be relevant. I think the point really is, do we reap here the opportunity of making this virtual anyway to also just broaden the audience to more than just the local ones, even if it's just for a handful of the meetings every couple of weeks or something like that?
These are good questions. I think so. I'm very happy with the attendance we got today, and that it's not too big and it's not too small. We didn't hit the 50-person Skype limit, but it also wasn't just 2 or 3 people. What I would propose for the future is, at least until we start to get to an unmanageable number of people, we can keep it open to everyone, and then longer term, if we really do generate a lot of interest, if people especially maybe are stuck at home and wanting to tune in and listen, I suspect a good strategy might be we keep the YouTube stream open to everyone, and then we keep the actual live chat more open to, or the Skype or Zoom or whatever we end up using, we keep that more for Hamburg people, maybe Helmholtz people, and then whoever we invite for that particular session, guest speakers, experts, and so on. That would be my initial proposal. I don't know what people think of that. I mean, at some point, it will get a little too big to just open it up to the entire public. But then I think having these 2 tiers might make a lot of sense. Okay, any other comments, questions? I'm curious what people would like to do next week in terms of papers or other topics. Does anyone have any suggestions? It could be as simple as, I tried to get this thing to work, it didn't work. Or it could be, I saw this paper, I've been meaning to read it, let's all discuss it together. I can say
So-
one topic that interests me a lot is convolutional networks that work on the sphere or approximations to the sphere. So if your image is defined not on a flat surface but on a sphere, then how do you do convolutions on it? And how can you use these to learn with spherical image-based inputs and outputs? So this could be an interesting topic for me, but maybe we do something interesting for someone else.
So my interest would be, what are the most suitable architectures for climate problems or climate-related problems? So because if you want to there is another option. You can do principal component analysis, which is might be better than convolutional network, and use principal components as inputs to the neural network. And my question: so what? So if there is a way how to determine the best strategy to tackle the climate problems, in terms of for instance, specifically in terms of neural networks.
Yeah, so this could also be interesting to look at, and maybe as a more general, less technical topic for Earth science, is to look at some of these challenge benchmark problems that are starting to emerge now, where someone says, okay, here's our goal. We want to predict weather with this time horizon. We want to predict these fields of temperature and pressure. What are the different methods that have been tried and how did they work? I think this could be an interesting topic as well. I think we could hopefully do it in a way which is general enough that people who are more interested in machine learning for other topics like material science or just in general in terms of computer science or mathematics are also going to find this interesting. So what I would propose is the following, is that if anyone wants to suggest any other topics for next week, which I think we'll do at the same time, 3 p.m. next Tuesday, I would suggest that they just, you can email me, you can email Marcel, I guess you could also email the group email list we've set up, and send us a suggestion anytime, but try to send it to us by Thursday night if you want us to use it next week. And Leonard, do you have a suggestion as well?
Yes, hi there. Can you hear me?
Yeah,
okay.
You're fine.
Great. I'm Leonard from Jerix in Hamburg, and I have maybe a little suggestion to make. So this may not be so relevant for most of you. I assume most of you are sitting in Geesthacht at HZG, but I thought that maybe it would be nice, so just that we get to know each other a little bit, that maybe every week someone could just give like a 5-minute pitch of the kind of problems he or she is working on. I think that would be really interesting to see who are the people that will participate in the seminar, what are their interests, and so on. And maybe that would be something that we could consider. Thank you.
That sounds like an excellent idea. I don't know if that was also you're volunteering to present your own stuff, but if so, that's great. If not, anyone who would like to do that, we could maybe have 3 or 4 of them next week to start off, and that would be really interesting.
Yeah, I'm just started with my project, but I would definitely like to present my plans. Just 5 minutes, tell you what I'm trying to do and what I think the problems are, and so on. Next week, very much.
Okay. That sounds like we have a first agenda item. We have a suggestion to keep the meeting time to under 1 hour. From the chat. I think that's not a bad idea. We're now at 1 hour 20. So I think we're still going to discuss the physics-informed neural networks paper from the same group. I think maybe if this is a good time, if anyone else wants to make general announcements or discussions or proposals, let's do that. But then I think we can wrap up the main part of the meeting in the next few minutes. Let me see if there's anything more on the YouTube chat as well. Don't think so. Oh, so someone did not have access to the paper, the science paper or the physics. So there should have been an email going out. But if you had someone just share this with you and did not get the email yourself, I will now share links to the papers as well. I'm going to drop them in the Skype chat and the YouTube chat. So there you go. Okay, so then if we don't have any more questions, I think this is a good time to wrap up the main meeting. And anyone who wants to stay for this more technical discussion is very welcome to do so. So thanks everyone for joining, and I hope to see you and some new colleagues next week. So I am now going to pull up this other more technical paper where this group really kind of explores the method a little more and sees what it can do. Marcel, do we still have you here, or have you lost your connection?
I'm still around.
That's good. Great.
At least sometimes when I have connection.
That's good. So this paper kind of goes through the same ideas. Again, we have the objective function in two parts. They do some other examples besides fluid dynamics. We've got the Schrodinger's equation right here. Where they impose this periodic boundary condition, which is pretty interesting, so that the value of the function should be the same at -5 and +5. They basically provide data on the initial condition, a bunch of points on the initial condition. They provide a bunch of points along the boundaries saying that not only should the function match on both sides, but the slope of the function should match on both sides. And then from this, you're able to compute a solution all the way through. It's a really nice example. They take this whole thing that we've done, that we've discussed with continuous time PDEs, and they also apply the same principle to discrete time steps. And normally you would do this with, say, some implicit or explicit method. In the explicit method, you're basically doing a fancy version of multiplying tendencies by time steps. This tends not to be numerically stable, especially for stiff systems. For implicit methods, it's more interesting, right? There you have these very stable numerical solvers. But you have to solve a system of nonlinear differential equations. And this limits the order, right? People see second, third, maybe even fifth order implicit solvers, but not much higher than that. What they do is, instead of solving the nonlinear system of equations, they basically say, no, we're just going to have a neural network output the solution, and then we'll check if that's correct, and then we'll feed back the errors during training. And they're able to use this to construct essentially a 100th order implicit Runge-Kutta solver, which is a really amazing thing that's never been done before. So they're basically able to get all of this, all of the evolution of this of this PDE over time at discrete time steps using, this is all one single implicit step with many sub-steps. So normally what you do is you go a short amount of time, you'd get a solution and then use it as your new initial condition. But what they do is they solve the nonlinear system of equations all the way through from 0 to the end. And they do this by training the neural network to satisfy the equations defining this Runge-Kutta tableau. This is a pretty interesting thing. They go on about how, well, because they're using a small time step and they're using a 100th order method, then they should have an error of 10 to the minus 20th. This is, I find it a little questionable because it's really big O of 10 to the minus 20th. Whether it's actually small is a different question. But they're able to use the same strategy with discrete time steps as well. They revisit the a cylinder example. This paper actually came first. They check how correct these pressure fields are. They estimate the physical constants as well from data. They do a lot of interesting stuff here. They do this Korteweg-de Vries equation, which has a third derivative of the state with respect to space, really using that auto-differentiation. Unlike most neural network training, they use large batch sizes and LBFGS instead of gradient descent or atom or something like that. This is interesting. There's a few interesting constraints on the architecture imposed by this method. So one very common strategy is to use these ReLU units, which are basically linear above, say, 0, and then they're 0 below 0. So they're basically rectifiers. And they can be very efficient for computation, and they work very well for a lot of problems. They don't work for this stuff at all. And the reason is this. We ultimately want to calculate, say, spatial derivatives of the neural network, saying if we change the inputs, the space inputs, the location input, how does the output change? And that effectively means taking the derivative of each layer with respect to its input, outputs with respect to inputs. But if you're using a ReLU unit, then actually the second derivative is 0 everywhere. So this forces them to use other kinds of neural network units like TANH, or they use this, I believe, Swish units. This is a different constraint. There's also other kinds of regularization. So they talk about their physics as a regularization, but you can't use this with, say, batch normalization or similar kinds of, you can't use this with dropout because it interferes with the learning of the physics. So they do this, and they run a lot of careful tests of, okay, how many points do we have where we observe the data, how many points do we check that the physics are correct. They generally just randomly sample the points to check the physics all along the domain, the solution domain. It might be better to do it some other way. Maybe some points are more interesting than others in constraining the network. And I think they're very open about how many questions this raises. Yeah, I don't know if anyone has other technical questions, how you would do this, how it would scale with different problems, how it's implemented, how it compares to other methods. So one question I'd like to pose, Marcel, maybe you have a thought on this too, is, so in general, we're training the neural network to output the local properties of the flow, concentration, pressure, flow velocity, as a function of space and time with a fixed initial condition, fixed boundary conditions. And I'm wondering, could you not provide initial or boundary conditions as inputs to the method? Could you not say, okay, given these initial conditions, what will be the local properties of the flow at this location and time, so that it would learn not just to solve one, but a whole range of possible different differential equations? Would that work? Is it sensible? Marcel, are you still in the chat?
I'm thinking about it. I think it would really, really complicate what you're trying to achieve here. Because in the basic case, what the network is trying to memorize in its weights is a surface, the value of an output variable of interest as a function of position and time. Now, if you also provide the initial conditions, you turn the problem into remembering something like a manifold of surfaces, a different surface for every different initial condition. Like going from a point estimate to a full distribution of solutions. It might be feasible with the right architecture, but it would certainly be a much more complicated thing to do. That said, you could probably, given that at least in this paper they use very small networks, maybe go all out with an approach like training hyper networks that spit out the small networks that then represent solutions to different initial conditions or even different physics.
That's a very interesting idea. I suppose it may depend on how one represents the initial conditions. You know, if, say, it's a one-dimensional case like in Burgers or Korteweg de Vries, like if the initial condition initially looks like something like one of these graphs here, well, you know, it's one thing if you have to represent the whole thing, and this is now a high-dimensional input, which makes it much more difficult to train the neural network to be ready for all the inputs it may receive. But if you have a low-dimensional representation of this initial condition, like maybe a few Fourier components or some, you know, very effective wavelet basis, maybe if you can represent it compactly, it does make it possible to do this. I'm not sure. Yeah, I don't know. Something I find a little puzzling about the way they pose their objective function is that they're adding together these different terms. Let's go to the more general case. Here we go. The data matching term and the physics term. What I find puzzling is that these basically have different units, right? So if your concentration, your state, U, has got some units, I don't know, let's say just density or mass or something, right? Well, okay, then this will be those, let's say grams. Let's say this is going to be in grams squared, this error term. But then the physics term, for all of these examples we saw, right, we have all the terms of, you know, the differential equation are essentially in units of, say then, grams or what have you per second. So this would be grams squared, this would be grams per second squared. And yet we just add them together. I would think it might make sense, depending on the problem, to tune the relative amplitude of both of these. Of course, if you're really able to solve the differential equation, you reduce both terms to zero, so it won't matter how you weight them. But in general, I wonder if it makes sense to do that, to kind of put more weight on the physics matching or the data matching. I suppose you may also want to estimate how reliable the data is or how much you trust the physical model. So It's not obvious to me that this is that just to add them together naively like this is the right way.
Is it possible that they use some kind of non-dimensionalized version of the equations?
Not that I could tell. Maybe I missed something in the text or the supplementary methods, but it doesn't seem to be. We could certainly check their code. If I can find it, yeah.
If I quickly may chime in on the question regarding the relative weighting.
Yeah.
I mean, it also depends on how much noise you assume to have on your observed data. Like you have the data term as we've seen in the main paper, and you've mentioned repeatedly that they only assume that it's corrupted by up to 1% noise. If you know that your data is noisier, you might want to increase the weight of the other term just to reflect the, essentially you're making a Gaussian noise assumption with the squared error term. And if you weight them the same, you assume that you have the same uncertainties over the physics as you have over the data, which in many cases is just not going to be given.
Makes sense. So this is a potential caveat when applying this method.
David? Hello?
Yes. Hi.
I think this is a more, well, it could be a more general problem. I'm thinking, for instance, in the data assimilation framework, by traditional methods, 4D bar or Kalman filter or something similar, you always have to, well, estimate at some point the uncertainty in the observational data that you are feeding in, and also the confidence in the model results. And for instance, in the Kalman filter wise assimilation methods, there are natural ways to, let's say, do this weighting through error covariance matrix. And I don't know in this setup with the neural networks if that would be possible, but in general, the problem is actually quite important, I would say, because actually the uncertainties in the data are not just limited, well, they are correlated in space and time. So in general, we'll have an error covariance matrix. And it's not so simple just to, well, rescale these cost functions or these two cost functions so that you have the same units. So that in general, the problem must be much, much more important.
Yes, I think that's a very good point. So, I mean, in terms of the math and the programming, I think it's pretty easy to replace this first term, the data matching term, with, you can include a covariance matrix, or you can even go further and say, I'm going to describe some general data likelihood, which may be non-Gaussian. If you can evaluate it in TensorFlow or whatever you're programming this in, given my predicted and observed, values, if I can calculate a log likelihood there, or a likelihood, then you can use anything you like. But the question is, can we actually get this for these different models? And it's not so obvious, yeah. Especially when you imagine, dealing with some more complex model from the physical sciences, where I think we discussed this earlier, where maybe you don't directly observe any of the flow variables, but something downstream of them through some additional model with its own parameterizations. It's not so clear. But in principle, if you can implement it, then the machine learning and mathematics and programming won't get in your way. Yeah. All right, so I think, one final point I would like to raise a question. I don't know if anyone has perspective on this, is, so what happens is you add more channels, more hidden variables. So if, I think I mentioned moisture and temperature. One could imagine other other variables you'd add if maybe this were a molecular simulation or an ecological simulation, or if we're doing chemistry, we're adding more and more variables to the outputs than just concentration. So as we do that, does the problem get easier or harder? I mean, we definitely have to have more outputs, so we have to train a more complicated network, and that may be more difficult and may take longer to train. On the other hand, as we add more variables, we may also have more equations relating them, so we may have a stronger constraint, stronger regularizations. So maybe it actually does scale well to many different variables. I don't know if anyone has perspective on this, or if anyone wants to say, oh, this is the model where I might try this, or a similar method. But yeah, go ahead. If anyone has something.
David, Eduardo again. Well, my feeling, just spontaneously, I would say that when we have more observations, and therefore we have to include a more, sorry, and we have to include a more complex model, then probably we will be able to reach, to train the network much more quickly, I would say. So the minimum will be reached by the algorithm more effectively, because actually the minimum is better defined physically, more constrained. Whereas if the problem is undetermined, because we don't have all the data that we need or all the equations that we need, well, then the minimum curve, let's say the error curve, would be broader and less well defined, so that to find that minimum will be perhaps mathematically more difficult. That will be my spontaneously what I
channels, we also add more observations as well, that we are able to observe those, or that they're just hidden channels?
Sorry, say it again.
So the question is, as we add more variables to the model at every point in space and time, are we able to make direct observations with or without noise, or can we only observe these indirectly through the inferred dynamics of the model?
Well, I think that the both problems are interconnected. Yeah, it's a good point. I would say that if we include, let's say we may have a very general model, or we would like to fit the observations that we have to a very complete model, or we may restrict ourselves to just a subset of the variables, and then we may need a simpler model. I don't know if that will be possible in every occasion,